Hello dear students, hope you all are safe and fine and very eager to study today's lesson. Today we shall study lesson 13 of science, that is magnetic effects of electric current for class 10th. But before we begin with our lesson, children, I would like to ask a few simple questions from you related to this topic that you might have already done in your previous classes. And answering these questions will help to refresh your mind. So children, are you ready to answer the questions? Here is my first question. Name the two poles of a magnet. And I hope children, all of you are familiar that every magnet has two poles and they are a north pole and a south pole. My next question, what is an electric current? And the correct answer is, the flow of charge is called an electric current. Yes children, now can you please tell me, what do you understand by the heating effect of electric current? Yes, the correct answer is that if in any conductor there is continuous supply of electric current, then heat is generated in it, and this is called as the heating effect of electric current. So children, let us see that what new we are going to learn in our today's lesson. Today we will learn about magnetic field and magnetic field lines. Then we will study about magnetic field due to a current carrying conductor and magnetic field due to a current through a straight conductor. Then we will discuss right hand thumb rule. Magnetic field due to a current through a circular loop. Force on a current carrying conductor in a magnetic field. Then we will discuss about electric motor, electromagnetic induction and electric generators. And in the last, we will study about domestic electric circuits. Let us begin with our lesson and see how to draw magnetic field lines of a bar magnet with the help of a compass needle. For this, take a bar magnet and a compass needle. Place the magnet on a sheet of white paper which is fixed on a drawing board using some adhesive material. Now, mark the boundary of the magnet. Place the compass near the north pole of the magnet and observe how does it behave. You will see that the south pole of the needle points towards the north pole of the magnet, while the north pole of the needle is directed away from the north pole of the magnet. Mark the positions of two ends of the needle with the help of a pencil. Now move the compass needle to a new position such that its south pole occupies the position previously occupied by its north pole. In this way, proceed step by step till you reach the south pole of the magnet. Join the points marked on the paper by a smooth curve. This curve represents a field line. Now repeat the above procedure by placing the compass needle near the south pole of the magnet and draw as many lines as you can. These lines represent the magnetic field around the magnet and are known as magnetic field lines. Children, let us now study about magnetic field due to a current carrying conductor. We know that a magnet attracts some materials towards it. We have seen in the activity that we have just now performed that if we bring a magnet near to a compass, then its needle gets deflected. Let us now see that how an electric current through a metallic conductor produces a magnetic field around it, and in which direction? For this activity, take a long straight copper wire and connect it with a cell in series pattern. As soon as we join the copper wire with the cell, the circuit gets completed. Now place the straight copper wire parallel to a compass needle. We will observe that the north pole of the needle of the compass gets deflected towards the east if the current in the circuit is flowing from north to south. This shows that the conducting wire behaves like a magnet and brings about a deflection in the needle. However, if the wire is disconnected from the cell, then no current will pass through this copper wire and it will no longer behave like a magnet, due to which the needle of the compass will come back to its original position. Now repeat this activity by changing the polarity. For this, interchange the connections of the two ends of the copper wire with those of the two terminals of the cell, as you are shown here. This will reverse the direction of flow of current through the copper wire. That is, it will now flow from south to north. Observe the change in the direction of deflection of the needle. You will see that now the needle is deflected towards the west. So we conclude that a change in the direction of electric current brings a change in the direction of magnetic field produced by it. Children, one very interesting thing to note here is that if we increase the distance between the compass and the current carrying conductor, then the deflection in the needle is reduced. This means that magnetic effect of a current carrying conductor on the compass depends upon the distance between the two. If the distance is more, deflection seen in the needle will be less, and if the distance is less, deflection will be more. Next, we will study about magnetic field due to a current through straight conductor. Children, the question here is that what determines the pattern of the magnetic field generated by a current through a conductor? Does the pattern depend on the shape of the conductor? Let us investigate this with the help of an activity. For this, we shall first consider the pattern of magnetic field around a straight conductor. Now to perform the activity, first of all, take a piece of rectangular cardboard and cover it with a sheet of white paper. Make a hole in the center of the cardboard and insert a thick copper wire through this central hole. Take care that the cardboard is fixed and does not slide up and down. Connect both the ends of the copper wire vertically and in series with battery with the help of connecting wires. Sprinkle some iron fillings uniformly on the cardboard. Allow the current to flow through the copper wire and gently tap the cardboard a few times. Observe the pattern formed by the iron fillings. You would find that the iron fillings align themselves, showing a pattern of concentric circles around the copper wire as soon as the current starts flowing through it. What do these concentric circles represent? Yes, they represent the magnetic field lines around the copper wire. To determine the direction of magnetic field lines, we can place a compass at any point over a circle. Observe carefully the direction of the needle. The direction of the north pole of the compass needle gives the direction of the magnetic field lines. And in this case, the direction of magnetic field lines is clockwise. Now repeat this activity after reversing the direction of electric current, and you will observe that magnetic field lines formed around the copper wire form the same kind of pattern of concentric circles, but now in anti-clockwise direction. Children, do you know what happens to the deflection of the compass needle placed at a given point if the current in the copper wire is changed? Yes, the deflection in the needle also changes. Secondly, if the current is increased, the deflection also increases. It indicates that the magnitude of the magnetic field increases if the current through the wire increases. A convenient way to find the direction of magnetic field associated with a current carrying conductor is to apply right hand thumb rule. So let us study what is right hand thumb rule. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field. Children, look at this picture carefully. Here the fingers of right hand are wrapped in anti-clockwise direction. Then, on applying right hand thumb rule, we see that the thumb, which is pointing in upward direction, is pointing in the direction of electric current. Next, let us study about magnetic field due to a current through a circular loop. Children, so far we have observed the pattern of magnetic field lines produced around a current carrying straight wire. Suppose this straight wire is bent in the form of a circular loop and a current is passed through it. Then how would the magnetic field lines produced by such a circular loop look like? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. That is, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. Similarly, at every point of a current carrying circular loop, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. By the time we reach at the center of the circular loop, the arcs of these big circles would appear as straight lines, and every point on the wire carrying current would give rise to the magnetic field appearing as straight lines at the center of the loop. To understand this, let us perform one activity. Take a rectangular cardboard and paste a sheet of white paper on it. Make two holes on the cardboard and label them as A and B. Now take such a kind of circular loop which has large number of turns in it. Insert this circular loop into the two holes in such a way that it gets fixed normal to the plane of the cardboard. Connect both the ends of the coil in series with a battery, a key and a rheostat. Now, with the help of a magnetic compass, draw magnetic field lines around hole A. You will observe that magnetic field lines form concentric circles around hole A, and the direction of this is anti-clockwise. Now, if you observe carefully, magnetic field lines form a pattern of same type of concentric circles around hole B as well, but here the direction is clockwise. The direction of magnetic field lines can be easily checked by applying the right hand thumb rule. In this activity, as you can see in the picture shown here, that the current is flowing in upward direction at point A. So, on applying right hand thumb rule, we can conclude that direction of magnetic field lines around point A will be anti-clockwise, and similarly the current flowing at point B is in downward direction. So, the direction of magnetic field lines around point B will be clockwise. Magnetic field due to a current in a solenoid. Children, let us first of all try to understand what is a solenoid. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. The length of this coil is always more than its diameter. On passing electric current through such a coil, it starts behaving like a magnet. Such a coil is termed as a solenoid. Now look at this picture of the solenoid carefully. You will observe that current is flowing in clockwise direction in the coil. That is why the left end of every turn of the coil behaves as the south pole, whereas the right end behaves as the north pole of the solenoid. Now, see children, we have reversed the direction of the current flowing through the coil. Now, again look at the picture carefully. Now, the current is flowing in anti-clockwise direction. So, now the right end will behave as south pole and the left end will behave as the north pole. We can reach such a situation when many small bar magnets are placed together with their opposite poles aligned with one another. All these together behave like a large and strong bar magnet. So, in this way, we can say that a solenoid behaves like a bar magnet. So, from the above discussion, we can conclude that if number of turns in a coil is increased, it will also increase the magnitude of the magnetic field produced by it, and also that the magnetic field produced across a solenoid is similar to that produced across a bar magnet. Children, let us now study about force on a current carrying conductor in a magnetic field. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor. French scientist André-Marie Ampère suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. The force due to magnetic field acting on a current carrying conductor can be demonstrated through an activity. For this, take a small aluminium rod and suspend it horizontally from a stand using two connecting wires. Place a strong horseshoe magnet in such a way that the aluminium rod lies between the two poles with the magnetic field directed upwards. For this, put the north pole of the magnet vertically below and south pole vertically above the aluminium rod. Connect the aluminium rod in series with a battery, a key and a rheostat. Now pass the current through the aluminium rod from end B to A. You will observe that the rod is displaced towards the left as soon as the current starts flowing through it. Now reverse the direction of the current flowing through the rod and observe the direction of displacement of the rod. Yes, children, now it has displaced towards the right. This activity suggests that a force is exerted on the current carrying conductor, which is aluminium rod in this case, when it is placed in a magnetic field. Then it also suggests that the direction of force exerted on the current carrying conductor depends both on the direction of the current and the direction of the magnetic field. Children, a very important point to note here is that the displacement of the rod is largest or the magnitude of the force is highest when the direction of the current is perpendicular to the direction of the magnetic field. Now, these three directions can be illustrated by a simple rule called Fleming's left-hand rule. According to this rule, stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular. If the first finger points in the direction of magnetic field and the second finger in the direction of the current, then the thumb will point in the direction of motion or the force acting on the conductor. Children, let us now study about electric motor. Electric motor is a rotating device that converts electrical energy to mechanical energy. Electric motor is used as an important component in electric fans, refrigerators, washing machines, computers, etc. It works on a principle that a current carrying conductor will experience a force when placed within a magnetic field. Let us now see how an electric motor works. An electric motor consists of a rectangular coil ABCD of insulated copper wire. The coil is placed between the two poles of a magnetic field such that the arms AB and CD are perpendicular to the direction of the magnetic field. The ends of the coil are connected to the two halves P and Q of a split ring. The inner sides of these halves are insulated and attached to an axle. The external conducting edges of P and Q touch two conducting stationary brushes X and Y respectively. Current in the coil ABCD enters from the battery through conducting brush X and flows back to the battery through brush Y. Notice that the current in arm AB of the coil flows from A to B, and in arm CD it flows from C to D. That means the direction of flow of current in arm AB is opposite to that in the arm CD. On applying Fleming's left-hand rule for knowing the direction of force, we find that the force acting on arm AB pushes it downwards, while the force acting on arm CD pushes it upwards. Thus, the coil and the axle mounted free to turn about an axis rotate anti-clockwise. A device that reverses the direction of flow of current through a circuit is called a commutator. In electric motors, the split ring acts as a commutator. The reversal of flow of current is necessary to reverse the direction of force acting on the two arms AB and CD and to complete a rotation. The commercial motors use an electromagnet in place of a permanent magnet. They have large number of turns of the conducting wire in the current carrying coil, and they have a soft iron core on which the coil is wrapped. The soft iron core plus the coil together is called an armature. This enhances the power of the motor. Children, now we will study about another device, that is electric generator. Electric generator is a device in which mechanical energy is used to produce electrical energy. Electric generator works on the principle of electromagnetic induction. According to this principle, if a coil is placed in such an area which has a changing magnetic field around it, then current is induced in that coil. In practice, we can induce current in a coil either by moving it in a magnetic field or by changing the magnetic field around it. Let us now see how an electric generator works. An electric generator consists of a rotating rectangular coil ABCD placed between the two poles of a permanent magnet. The two ends of this coil are connected to the two rings R1 and R2. The inner side of these rings are made insulated. The two conducting stationary brushes B1 and B2 are kept pressed separately on the rings R1 and R2 respectively. The two rings R1 and R2 are internally attached to an axle. The axle may be mechanically rotated from outside to rotate the coil inside the magnetic field. Outer ends of the two brushes are connected to the galvanometer to show the flow of current in the given external circuit. When the axle attached to the two rings is rotated, then the arm AB moves up and the arm CD moves down in the magnetic field produced by the permanent magnet. In this way, the coil ABCD gets rotated clockwise. By applying Fleming's right-hand rule, the induced currents which are set up in these arms move along the directions AB and CD. Thus, an induced current flows in the direction ABCD. If there are large number of turns in the coil, the current generated in each turn adds up to give a large current through the coil. This means that the current in the external circuit flows from B2 to B1. After half a rotation, arm CD starts moving up and AB moves down. As a result, the direction of the induced currents in both the arms change, giving rise to the net induced current in the directions DCBA. The current in the external circuit now flows from B1 to B2. Thus, after every half rotation, the polarity of the current in the respective arms keeps changing. Such a current which changes direction after equal intervals of time is called an alternating current or simply AC, and the device is called AC generator. To get a direct current or DC, a split ring type commutator is used. DC means a current which does not change its direction with time. For this, one brush is at all times kept in contact with the arm moving up in the field, while the other brush is always kept in contact with the arm moving down. We have seen the working of a split ring commutator in the case of an electric motor. Thus, with this kind of arrangement, a unidirectional current is produced. This type of generator is called a DC generator. Children, lastly, let us discuss about domestic electric circuits. In our homes, we receive supply of electric power through a main supply, either supported by overhead electric poles or by underground cables. One of the wires in this supply, usually with red insulation cover, is called live wire or positive wire. Another wire with black insulation is called neutral wire or negative wire. In our country, the potential difference between the two wires is 220 volts. At the meter board in the house, these wires pass into an electricity meter through a main fuse. Through the main switch, they are connected to the line wires in the house. These wires supply electricity to separate circuits within the house. Often, two separate circuits are used. One of 15 ampere current rating for appliances with higher power ratings such as geysers, air coolers, etc. The other circuit is 5 ampere current rating for fans, bulbs, etc. The earth wire, which has insulation of green color, is usually connected to a metal plate deep in the earth near the house. This is used as a safety measure, especially for those appliances that have a metallic body like electric press, toaster, table fan, refrigerator, etc. Children, when high power rating electrical appliances are switched on simultaneously, overloading can occur, or sometimes the live wire and the neutral wire come into direct contact when the insulation of wires is damaged. In such situations, the current in the circuit abruptly increases. This is called short circuiting, and the use of electric fuse prevents the chances of short circuiting. Let us now quickly revise whatever we have learnt in our chapter. Today we have learned that a compass needle is a small magnet. Its one end, which points towards north, is the north pole, and the other end, which points towards the south, is the south pole. A magnetic field exists in the region surrounding a magnet, in which the force of a magnet can be detected. Field lines are used to represent a magnetic field. Right hand thumb rule is used to find the direction of magnetic field associated with a current carrying straight conductor. Electric motor is a device which converts electrical energy to mechanical energy. Electric generator is a device which uses mechanical energy to generate electrical energy. Now I will ask you some questions is in the form of a fill up and you have to fill the correct answer in the given blank space. A compass needle is a small dash and the correct answer is magnet. A compass needle is a small magnet. And your last question is that you have to tell whether the given statement is true or false. So the statement is, an electric motor converts mechanical energy to electrical energy. Yes, children. What is the answer? Yes, this statement is wrong or false because an electric motor converts electrical energy to mechanical energy. With this, we come to the end of our today's lesson, that is magnetic effect of electric current. I hope, children, you must have enjoyed learning the lesson with me. We will soon meet again with the next lesson. Till then, take good care of yourself. Goodbye and thank you.